So, welcome back from the coffee break. Our next talk is by Juan Berner. He's talking about web application firewalls and how to use them without screwing over your users while still being able to block attacks. Give a warm welcome to Juan.
Thank you. Hello. Okay. Well, welcome everyone. So yeah, this talk is called Building Your Own WAF as a Service and Forgetting About False Positives. A bit about me. I'm Juan Berner. I'm a lead security developer at Booking.com. That's my Twitter and my Medium. I usually like dealing with challenging problems at scale. And this is one that actually fit very nicely into this. But first, let's talk a bit about what a WAF is. So WAF stands for Web Application Firewall. This is mainly used to protect against application attacks. Depending on which type of WAF, you might have other types of capabilities. And when we're talking about web application attacks, you can think about SQL injection, remote code execution, HTTP protocol violations, rate limiting, that kind of stuff. So first I want to talk a bit about how WAFs are usually deployed. So a WAF can be deployed in an inline mode. This means that it's in the middle of the traffic between your web application and your clients. Some pros for this is that you can do traffic inspection, you have the ability to block, and it's pretty transparent for web servers because from their perspective, not much has changed. The negative parts on this is the network placement. It can be very hard, especially when you're dealing with a huge network of multiple data centers all over the world. And the latency can also be an issue. Depending on which inline mode you use, you might have more latency or less latency. But in the end, you're adding an extra hop in the middle of your users. And one more thing is that also this is another possible failure point that you can have between your application and your customers. Another approach to this is using an out-of-band mode. This basically means that you are looking at the traffic, and this is still transparent for web servers, and a bit simpler to set up since you no longer need to have it in the middle of the traffic itself. But of course, you can't block attacks, and you have other issues, like for example, with perfect forward secrecy, where if you're in the middle of the traffic, you can do some stuff like terminating the connection and starting the connection again, like a bit of man in the middle. But out of band, you might not be able to deal with that. A newer deployment mode is using an agent. This basically means that you have a piece of software running in the same box as your application, and this is acting as some sort of proxy. This is quite simpler to scale and, of course, easier to set up from the network. You just, OK, if you're building a box, whatever you're using Puppet, Chef, OK, just also run the agent there. Now, this can be a lot more invasive. You have a piece of software running on the same box as your web application. So if there are any issues with CPU, any issues with RAM, then that might also affect your application itself. And it can also be less efficient on resource allocation, since suddenly when you scale horizontally, if you have an application that just needs, like, let's say, 1 gig of RAM and an agent that needs a lot more of RAM, then that means that you might need to scale horizontally in not a super efficient manner. And one of the latest approaches is the cloud. So in this case, it's quite simple to set up. And you have a huge network effect because only these providers, which are basically the cloud is somebody else's computer. So they're providing you the ability to get your traffic, clean it, and send it back to you without these attacks. But of course, this means that you are basically trusting a third party with all your traffic. And it can add a bit more latency, or quite a bit more latency than the other solutions, given that you're actually going through somebody else's data center before getting back to your data center. This is a bit simpler if you are actually already on the cloud, but in the cases on-premise, it's that case. So I mentioned the different deployments, and there are some caveats with these solutions, like, for example, network placement. That can be a big deal in most of this. And the false positive rate which is kind of an issue with most of the WAFs, basically because when you have a particular matching rule on the WAF and somebody is doing some legitimate action, which is actually triggering that matching rule, it might block that as an attack instead of realizing that this is actually a customer and this is not an SQL injection attempt. They're just sending a message. And there's also the issue of control for developers. It's quite normal that when you have a web application firewall, and as soon as at one time that web application firewall causes any issue, developers are always going to blame first the web application firewall. So is there more latency? Maybe the WAF is adding latency. Are users complaining? Maybe the WAF is blocking them, or it's doing something with our headers, that's something with our resources. So that's usually a point with developers which can have a lot of friction in introducing these technologies. So how did I arrive at this issue? So I was working on application security, and I was looking into introducing a WAF, but it was quite a challenging environment. There was no acceptance for false positives. There couldn't be users affected by any solution, which really reduced the amount of solutions we could use. There was a lot of reluctance towards commercial applications on a very, let's say, open source environment where people knew very well what was going on, were able to dig into the code when something was going on. Then having a commercial appliance, which is basically a black box between your users and your web servers, was not something, let's say, appreciated. And then one of the requirements was that the blocking could only happen through the application. This means that the application itself would decide if they want to block or not, and this would go into the whole, let's say, metric system of the application itself. So that developers themselves can really understand what's going on. And of course, latency was a huge issue. So suddenly adding tens of milliseconds to every single request was not an option. So I ended up with this approach of building the WAF as a service, which I will go into details, but basically looking into these different problems and solving them. So for example, the false positive rate, instead of just treating each event as a single event to consider, getting the context around each event to be able to decide if you want to block it or not. Not using an appliance, but an API call, which is something that developers are very used to, just interacting with a web service. Blocking behavior will be decided by the application themselves. Depending if you use a library or an agent, this might change how they decide it, but in the end, the application itself would know, okay, how they want to treat something they want to block. And of course, removing the latency for regular users, which was one of the biggest pain points here. So to give some statistics on this, we're talking about 4 million requests blocked each month, about 5,000 distinct fingerprints, which are automatically detected and then blocked. No latency added for regular users, and as far as we know, and we check and we have review systems, no known affected users through blocking false positives. So this talk is about how you could build one. So there are a lot of open source components that already exist, and there are some requirements to do something like this. You basically need a log processing pipeline. So if you have looked into ELK, so Elasticsearch, Logstash, and Kibana, that's pretty much it. You need to be able to build a WAF API, so a web service that's going to act as the WAF, and you might create some kind of library or an agent to interact with that WAF and the application itself. So for this talk, I decided to create a study case. So I was working with Google Cloud on some of my personal projects, so I set up Terraform recipe on Google Cloud, which basically creates what I'm going to talk into whatever Google Cloud project you have with all these components, so you can actually test it yourself, and I will do a demo on that. But basically, this is a simple, and I'm going to talk about this as the study case, a simple web application, which is going to have the WAF as a service to be able to protect itself, and all the components needed for this to happen. So now the question is on the deployment mode. How are we going to do it? I already mentioned the different alternatives, but there's two big ones that usually come up. One is the out-of-band mode. As I mentioned, the problem with this is that you cannot block. So in this case, we will have our demo web app. Then each time a customer makes a request, this would go as a log into our pipeline. Here I'm using PubSub, which is a system from Google Cloud to be able to publish and subscribe messages. And then there is a data flow, which allows you to actually process the messages, and eventually will go to Elasticsearch. So this is great. This gives you visibility on the attacks that are going on, but you cannot do much about it. Inline mode, in this case, we can do stuff about it because we are blocking in every single request. But as I mentioned, now you have the problems about false positives, and you have the problems on the latency, which is added for every single user. And to keep in mind, every application is different, especially when you're dealing with a huge environment with multiple different applications. Each application might have a different threat model. They might have different false positive tolerance, which might depend even up to the different endpoints. And they might have also different risk acceptance. Some applications might need to have every single request reviewed, while others might be fine, OK, we just want it out of band to be able to review it for a while. And this was a bit about finding a middle ground. So the out-of-band would remove the latency concerns, but we need some kind of inline possibility, so we are able to actually block on every single attack. And this is the question, how can we get the best of both worlds? So we can block, but not affect our customers with false positives or add latency. This is how it ended up in this kind of hybrid mode. So this means that there will be some requests which are going to be in inline mode, other requests will be in out-of-band mode, and most of the requests are going to be evaluated through time and through different types of rules, which can be fingerprint rules or traffic rules. I will go into that later. They will end up being in an inline mode or out-of-band mode, which essentially means that the traffic that you want inline is going to end up inline. The traffic that you do not want inline, like regular customers, is going to behave in an out-of-band mode. So let me go a bit into the different components of this solution. So the first is the web application. That's what we want to protect. This is the one that developers control, so they're able to decide if they want this application to be in inline mode or out-of-band mode based on their risk acceptance. And this is going to be sending logs with partial information about the request encrypted, so that we can actually, out-of-band, replay that information against the web application firewall and know if this was an attack or not. And as an example, using a Flask API in this case. Now, this web application, as I mentioned, is to interact with the web application firewall. And there's two different modes in which this can be deployed. One is using an agent, which is just a very simple proxy, which is going to be between the customer and the web application itself, with minimal footprint on the server. And this would just be able to talk with the application to decide how they want to block things, and talk with the web application firewall to review if the request or the response is triggering any of the web application firewall rules. And this is a bit how it would look like. So basically, you have the customer, it sends a request. The agent first might request to a web application firewall, OK, is this an attack or not? And the same with the response, depending on the different rules that I mentioned. Now, a simpler approach is just a library. This is simpler to implement. Problem is, if you have multiple languages, you might need to implement it in all of them. But in the end, this is just a REST API. So you can use Swagger. There are a lot of tools for this. This has inherent risks, which are that since it's an API call, which is happening in the application itself, that means that then, for example, let's say you have the Django application. Once you're adding, OK, I'm getting the request, I want to actually call the WAF API. At that point, you could have your Django framework compromised. So that might be too late. Depending on your risk acceptance, this might be fine or not. But there's the problems of having with a library instead of just having an agent, which at least you could say, OK, have a minimal code base, so it's harder for it to be compromised. But this is the strategy I will use for this talk and for the code I'm going to have published on GitHub. And I will have it as one of the last slides. Now, another key component here to be able to reduce the false positive rate is going to have a historical database. In this case, I'm using Google BigQuery, which is aimed at dealing with petabytes of storage. Depending on what size of your environment is, you might not need to handle petabytes, but this scales quite nicely. And the idea is that this historical database is going to be able to give you insights on not just the context, but the history of these particular endpoints. So you can imagine on pattern of behaviors of false positives. This is an endpoint that usually has a lot of detection false positives, which I will go into details afterwards, what I mean by detection versus blocking the false positives. Or is there business value on this request which is coming in? It's coming from a particular customer or not. So another component is going to be a state store. In this case, I'm using Redis because it's quite fast for doing lookups. I'm also using it to store the configuration. But the idea is that this is going to be a component that needs to be quite fast so that web applications can get information from there, in some cases cache it locally, so that then you reduce the amount of requests you need to the web application firewall. Now I mentioned that we will be consuming a lot of logs. So I already mentioned PubSub. This is a component that will serve for the publishing and subscriber mechanism that we want web servers to be able to publish logs. And then we want our processing framework to actually consume those logs, which when I say logs, you can imagine request information. Now, when we get those logs, which have the request information, we will need to actually process them. In this case, I'm using Google Dataflow, which is a parallel processing framework. This allows you to scale horizontally as much as you want on the processing part. And this is the part that's going to get requests. And in the case that a request has not gone inline through a web application firewall, this is going to replay against the web application firewall the same request and get back as a response, OK, this request is actually a web application attack or not. And how we can work with this is that we can have scoring around the particular attack. So in this case, for example, we might want to create some sliding windows of time. So you can imagine this is a bit of how windowing might work, but the idea is that we might get a particular, let's say, fingerprint and evaluate over a minute with a sliding window of 1 second each. So you can get every second a different chunk of that window of 1 minute and be able to tell, OK, how many attacks have happened in this minute for this particular fingerprint, for example. And this is a bit how the diagram, the DAG, looks for this particular data flow job. Basically, what's going on here is that we are consuming all the events from PubSub. We are replaying the request against the web application firewall service. And then, in some cases, we are doing correlations to detect, OK, is this an attack that's going on? And I need to update some information to my state storage, so Redis, for example. And in other cases, I want to write these events to BigQuery for historical analysis, or I just want to send them to Elasticsearch. So this is a bit how it looks. Basically, we have the web application, which might be doing requests to the web application firewall service. But then, in some case, in the cases where it's not happening, it's actually Dataflow, which is doing the same exact request. The end result is that all the requests are being evaluated by the web application firewall. And this data flow component during these windows and scoring might trigger let's say, suspicious activity that a detection component can evaluate and then decide, OK, suddenly this traffic, this needs to go inline. So that's mostly on how do we get to the WAF service. So the WAF service is the key part here because it's going to be the service that actually tells our application, or for example, Dataflow, that this is an attack going on. And there's some neat advantages of architecting it in this way. So now, since it's a service, you can actually have it with a pluggable architecture where you could have different components behind that WAF service itself. Those components can be parallel, and then you can actually tell the application, OK, this is this particular component that we have is saying that this might be an attack, and the application can decide how to react. In the same way, the application might decide, OK, which kind of web application, this WAF API, which kind of components do we want to run for my application itself? So I will explain a bit what I mean by different components. So let's say, for example, that you have your WAF API, and you want to start adding some normal web application controls from open source components. So there's two very common web application firewalls, which are open source, which is Naxi or Mod Security. In this case, I'm using Mod Security. But you can just pick one of those, or both. Then you can have your own custom modules. So let's say that you want to implement some particular rules that there's no open source alternative that can actually give you this value, but you want to evaluate every single request for something that applies to your business logic. Maybe you're doing a database call and reviewing something in particular. Maybe you're implementing some kind of rate limiting service or a particular rule engine. Or, for example, in some cases, you might have your own machine learning models that you want to evaluate against particular request or all requests and get a prediction based on it. And then, of course, you have proprietary software. So you might say, I have a commercial WAF that I really like, and you might place it as one of these components. The key thing here is that you can put as many ones as you want. And for example, if you are doing an evaluation and you say, OK, I have 3 of the main web application firewalls, it's quite simple for you to just place them all behind the web application firewall service. Even if you don't trust them, you just say, OK, I'm going to work with them only on the out-of-band approach, which means that suddenly every single request is going to be evaluated by these 3 different web application firewalls, and you can very nicely evaluate, OK, this one is getting 80%, this one is getting 70%, and this other one is missing all of the attacks that we know of, for example. So let's go to a particular component example. So let's say Mod Security. I looked into Mod Security because it looked like one of the best open source web application firewalls. And it has the libmod security library. But for this example, what I'm doing, instead of using the libmod security to be able to interact and be able to decide this is an attack or not from the API, I'm actually changing how mod security works to make it an API. So mod security is going to, instead of how it usually works, that it's just get the mod security writes logs with all the attacks, I'm going to make it return the information on the attack. So this is accomplished by adding a simple rule to mod security, which says after all the rules have been evaluated, I want you to check if there's any rule that actually triggered anything, which I'm storing every single rule in one of mod security variables, and then output, or basically append to the output of the web application the results of those rules, which basically means that mod security is now, if you have a dummy web server behind mod security or in mod security, you are just getting as a response whatever mod security detects as an attack, which means that then your application, the WAF API, can actually use it to decide, basically. And for the response, it can be a bit trickier, but basically what you're doing is you are going to tell mod security through a CGI, which is going to get the content of the web application, for example, and it's going to respond that content as if it was the content of the CGI, which means that mod security is going to evaluate that content as part of their own rule set. So if, for example, the web application was responding, let's say, dump of a database, then that information would go through the API. The API would use then the CGI, so mod security would be able to look at that response and say, OK, this is actually a dump of a database, so I consider this as an attack. So this is actually how it looks like. You basically have the WAF API, and behind the scenes, there are multiple components. So here I have 3 examples. So you can imagine rate limiter is something that you wrote yourself, so some Python script. Mod security, you are using the open source component. And then you add a machine learning model that you need. The point here is that you can add as many as you want due to the parallel nature. And this means that the latency of the API is going to be as low as the slowest component that you have, since you can do it all as asynchronous calls. OK, so now the question is, how do we actually block this? Do we block attacks? So there's the main thing here is that we need to decide when do we want to send the traffic through a WAF versus when we want to just observe the traffic. And this can be manually or automatically. So let's start a bit with traffic routing, which is the way where we are going to decide if we want to send traffic or not through the web application firewall. One of the ways to do this is fingerprint-based. So when I was talking about the data flow component, data component is going to examine each request. It's going to create multiple fingerprints based on different information on the request itself. And it's going to be able to find patterns among them to be able to say, OK, this particular combination of parts of the request, I consider this a particular fingerprint. So you can imagine as an IP address, a client ID, a particular cookie identifier. And then based on scores, which you are going to determine, you will be able to decide, OK, this particular traffic which I'm seeing, I'm going to start routing it through the web application firewall. Another option is using net blocks. So you can imagine as particular ISPs which have bad reputation, or you have seen bad reputation from them in the past to your application. You can think about hosting providers, which usually don't go to your web application itself. So it's mostly people trying to scan it and find vulnerabilities. Or, for example, Tor exit nodes, proxies, not because they're bad inherently, but just because you can see a greater amount of abuse, at which point you might be willing to accept some latency for those net blocks, for example. And then another option on traffic routing, and this doesn't mean it's all of them, but this is some of the key ones that I have worked with, is virtual patching. So let's say that you get a call at 3 a.m. and somebody tells you that there's an SQL injection in one of the endpoints of your application. You cannot actually immediately roll out a fix, maybe because the fix is very hard, maybe your deployment can take a lot of time. But you can immediately, if your web application firewall API is able to detect this attack, or you want to write a custom rule for it, you just add virtual patching for this particular endpoint or combination of endpoint and parameters. Which means that essentially, suddenly, this web application, the web application, one particular web application in this case, would start routing all the traffic for that particular endpoint and parameters through the WAF API. So that was mostly on how do we avoid latency, which there are some caveats to that, and I will talk about it later. But the main thing there is that we are ensuring that most of our customers are not going to be affected by the web application firewall API latency. But the other point is the false positive rate management. So how do we ensure that when we go to a developer and we say, OK, we are going to have this percentage of false positives, and they're like, no, we actually need lower than that. If not, we cannot use the firewall, that we actually can guarantee it. So here I want to make a difference between detection false positives and blocking false positives. So detection false positive would be mod security detects I sleep for 2 days as an SQL injection, because it just looked at sleep. It's not that way, but it could happen something like that. That would be a detection of false positive. But what I'm aiming at not having is blocking false positives, which means a customer goes to a website, writes, I will sleep for 2 days tomorrow, and then they get blocked because of that message. That's the part where we are trying to avoid. And the key to doing this is to allow the blocking without impacting the customers and at an acceptable rate that will be defined by the application. So there are some components we have to take into account to accomplish this. One is the business logic. So for example, how trustworthy is the user and IP address? This is a bit where the historical analysis would help also, but also key business activity and what would be the impact on blocking them. Some things are going to reduce the risk on a blocking false positive. Then, of course, the historical analysis. So how normal is this kind of detection false positive for a particular endpoint if I'm seeing something that a priori you think it might be a detection false positive? Then how does this user compare to others? And how common are detection false positives in this endpoint? But for example, let's say that you suddenly see a couple of requests which look like an attack. You might want to evaluate, OK, is this a particular user, or is this all users in this particular endpoint? That might actually mean that there has been a new release, which is triggering detection false positives, and you need to go to, let's say, mod security and tune the rules. And one which is key is the context analysis. So how many times have they triggered one of these detection false positives? And for how many requests have they sent? So information that's happening on the context, which a lot of these solutions do not take into account so much the context, but in this case, it's going to be critical. So let's do an example. So let's say that we have a chat, and somebody places, I sleep 1 or 2 days. And it might be detected as an SQL injection. Maybe we have a bad rule there, because it's just looking at sleep, parentheses, integer, and that's it. Now, we are going to work with the assumption that the probability of this kind of false positives are independent between each other. So then we decide, OK, for this particular application, based on the risk that we have, we want to have 0.00001% of false positives for SQL injection. And we have a 0.1% of probability of getting one of these false positives, which is super high. But this basically means that, OK, we decide we want a score of 5 over a window of 1 minute or 30 seconds, which basically means that somebody has to trigger 5 of these possible SQL injection attempts in 30 seconds or 5 minutes or whatever window you want to be considered as a possible attack. At which point, you would start routing all the traffic for this particular fingerprint through the WAF, web application firewall. And of course, this is aimed at attacks that need volume. So you can imagine that SQL injections, they usually need a lot of requests to be able to actually find something, so they need to test a lot, especially if you are mostly concerned on blind SQL injections, which are going to have to do a lot of requests to be able to exfiltrate data, for example. But this will depend on the risk acceptance that you have and how you decide scoring. In some cases, you might say, we can't have any kind of scoring, we need it immediately. So at that point, that was how we decide, OK, how we make sure that the false positive rate is whatever we want, based on the context analysis. And the other tools I mentioned, as the business and historical analysis, allows you to reduce even further the probability of false positives, or at least ensure that the risk on the business impact is going to be low enough at the point you might want some human intervention when that happens. But the last part is, how do we actually visualize this information? So for this, I'm going with Elasticsearch Logs as Kibana. This gives you the ability to visualize the activity that's going on, what is actually going inline, what is going out of band, some metrics around the solution itself, how much latency is it adding to users, how much is it taking to process, what are the scoring, and the different types of modes between the different applications. So this is how it looks. This is a picture of the setup that I have in GitHub. So basically, it's the normal stuff. We have a couple of IPs, different types of attacks that are going on, different types of plugins that are working with this. And in this case, for example, the different attack modes and states. So for example, here, it's not very readable with the slides, but you can see that most of the traffic is going through a replay mode, which means that most of the traffic is going out of band, and only a small section is actually going through inline mode, because this is working on the fingerprint-based mode, which means that only when it detects that an attack is going on, and that might be after 2 seconds or 5 seconds in production state. In this case, I'm using the smallest Google Cloud box to handle all this architecture, which means it takes quite a lot. But in a production state, you can get it up to 2 seconds to be able to detect attacks. And one point with that is that it might not be acceptable for every application, but if your application can accept some delay and can accept that, for example, nobody's going to come with a particular vulnerability without knowing anything, just trigger it and just dump all your database in one single request, then this mode will be able to remove almost or all false positives. In our case, all false positives from the blocking perspective. And to give you an idea, in this case, for example, I implemented just 3 different components for the web application firewall service. So there's one which is a rule engine, which is basically something that you can say, OK, for example, this particular IP address, I want it always going through the web application firewall. That means that suddenly the web server gets in its cache an update, and every time it sees a request, OK, I send it through the web application firewall. Then another one is the rate limiter. So I did a simple rate limiter to be able to say, OK, this is the maximum amount of requests that should be allowed, at which point, if you are in the out-of-band mode and you're not inline, when it sees that some particular fingerprint or collection of fingerprints is getting close to that limit, it's going to immediately update the web servers and say, OK, for these particular ones, they're quite close, so keep looking at them in inline mode, so that when they hit the limit, you're actually blocking them. And then, of course, I add also mod security to have visibility on web application attacks. So in this case, we can see the match data for an SQL injection. I just have like SQL map running quite slowly there. And the point is that what's going on there is that the web application firewall service is doing an API call to an Apache running mod security, and that Apache is actually returning all the information that mod security detects on the request and the response. So yeah, and for this, I built a simple management tool, which allows to visualize these different the ways to manage this kind of architecture. So I'm sorry for the display, it's not super nice, but basically this means that you have the ability to say, okay, on the request stage, so when our web application is getting a request, do we want it to have any interaction with the WAF at all? Maybe you just want it disabled and being out of band. Do you want to work it on the fingerprint mode, which I call it identifier there, which means that when Dataflow is looking at all this traffic, it's going to calculate scoring, and it's going to decide, okay, this particular traffic needs to be, this particular fingerprint needs to go through the WAF. So that immediately makes the web application send the traffic there. Or do you want to go it on full mode, which means that every single request we're going to go through the WAF. Now, the same can happen for the response. And then I added the capability of WAF proxy routing, which means that when a web application, either the library or the agent, gets a request, it can check based on the information of the IP address using IP address database, if this is considered a proxy or a Tor exit node, in which case it's going to route all the traffic through a WAF. The same way you can say particular, let's say, countries. In the example that you might have a web application which is only for a particular country, and most of the traffic is from that country, you might say, okay, for the rest of the world, we can accept some latency in that case. And the scoring threshold. This basically is going to decide what's the acceptance of false positives on blockings that you want. And I have to clarify something here. When I say that you're going to say this particular fingerprint is now going to be blocked, it doesn't mean that suddenly all the traffic is blocked. This just means that this particular fingerprint, now it's adding latency to every single request, which now means that every single request is going to be evaluated through different plugins. And you might also be able to say, for example, which actually increases a lot the probability of not getting any false positives, that once you detect something that looks like remote code execution going on from a particular fingerprint, you are going to make that fingerprint go through a web application firewall, but only to block things which also look like remote code execution. So not to block for everything. Which means that even if you have, let's say, a very high false positive rate from your web application firewall solution, like mod security, if it's not just the probability now that, okay, somebody might have done 5 possible remote code execution, but then they get blocked for a SQL injection, which was a false positive, it will only block them for the remote code execution. If they now start with SQL map, then they would start getting blocked by, for the SQL injections. So this is mostly aimed at almost getting all the false positives out of the picture. And the inherent risk with this, as I mentioned, is that if you are actually looking at an application that maybe somebody's doing 10,000 requests in a single second, or there's a particular vulnerability which is widely known, then in those cases, that's where you should use virtual patching. Or if this is a risk that you cannot accept, then you would need to go full inline mode. This is mostly for applications that can accept that risk of, for example, somebody having to do more than 5 requests in 1 second to be able to find a vulnerability on your web application. And yeah, so here you also have the identifier-based routing. So in this case, 2 IP addresses which were detected, virtual patching, for example, for the ping endpoint, and a block rule for a user agent. And finally, rate limits. This is just to show some examples on what can be made. There's a lot of possibility for you to add everything that you might need. So there are a lot of different solutions that you might be interested in, like bot detection, or developing your own in-house detections based on your application or threats that you're interested, that you can use to extend this. So to go over this, basically, the benefits from this approach is that it can reduce the latency. It can add a lot of flexibility on how you want to manage each application. And you can decide the false positive rate. Based on each application, based on each threat model and risk acceptance, you can decide which false positive rate you want. And the caveat, of course, is that there's a delay time for blocking. And this is the big one. Basically, you are saying, OK, if somebody starts doing an attack, there's this amount of seconds until I can start deciding to block it, if it's not going through something that you were already blocked. Once you find a fingerprint, you can leave it there for as much time as you want. You can leave it for 1 day, for 1 hour. But this also adds complexity in the solution. Because suddenly you are not going out of band, you're not going inline, you're actually doing both, depending on automatic rules or manual rules you are adding on the fly. So yeah, that's it. And I will try now to do a demo, if it works. So basically what I did was I got an instance on Google Cloud. Maybe I can show a bit more on this. Oh, yeah. Is it fine now? Can you read? So basically, what I have here is a Kubernetes cluster of a single node, and I'm running a scanner, which is basically just doing SQL injections all the time. I'm running Redis, which is the storage, Logstash, Kibana, and Elasticsearch for visualization, demo web application, and a larger component, which is going to get all the information from Dataflow and decide, OK, I'm going to do a query to BigQuery. I'm going to look for the history of this endpoint and decide if I want to have a higher scoring to block or a lower score to block. And of course, the WAF API. So for example, I'm now on the WAF API, and I'm going to show the configuration that's currently there. So basically, I have everything disabled. There's the this is IP address is the scanner, which is always scanning. So it detected that, but it's not blocking it. It just knows that something is off with that. So I have some notes here. So remember, basically, first, I can show you that this is the web application that we're talking about. I'm doing an SQL injection. It doesn't get blocked. That's expected because we are in non-blocking mode. Now, what I'm going to do is I'm going to change the mode so that it's now on full mode. So this basically means that every single request is going to go through the WAF. Now it gets blocked, basically. Now I will disable this, and I will move this. Well, I will just move this into identifier mode. This basically means that now it should only get blocked if we see enough activity to trigger a score. So now this is working. I'm going to trigger a lot of requests. And basically, now the big issue is that in this setup, Dataflow is not very fast. So it takes quite a while until it's processing. But if you have worked with streaming of logs at any point, and if you think about using Kafka and whatever processing you have used, then this is just from 2 to 5 seconds in a production environment. And now it got blocked. Basically, what happened here is that I started doing SQL injections. These requests were out of band, going through the web application firewall service. It got to the point where the score that they returned was high enough, so above the scoring threshold of 5, that it detected that my IP address, in particular, was doing this behavior. It was added as a fingerprint that needs to be blocked, and now it's getting blocked, basically. So now I can also show you an example on virtual patching. So I will just delete all the identifiers, which means that now if I do a request here, I'm fine, because I'm no longer considered a bad fingerprint. But in the same way, let's say that we go to ping, and I'm going to also do some kind of SQL injection here. This is fine. But let's say that we say, OK, we know that this ping endpoint is vulnerable, so it has attacks. So what we basically do is, OK, we will add as a virtual patching endpoint the ping endpoint, which means that now the configuration, there's no IP address here, but my endpoint is patched, which means that now I'm blocked. So this is all in GitHub. And basically, let me see. So it's there in GitHub. You can just run that command, clone it, and run it on your own GCP project, and you're good to go. It's the same thing I'm just showing. And you can play with it if you are interested. Any questions?
One question is fine, because we're running out of time here.
What are the identifiers you use most, and how effective are they? Like in terms of user agent, session, IP. Like what do you tend to be matching on the most in production?
I'm not sure I can say which ones I'm using, but I can tell you that something that's very surprising to me is that IP address is quite effective, because most of scanning solutions for web application attacks do not actually use a lot of different IP addresses. Most of the attacks are usually coming from a single IP address, but the whole point is that you shouldn't just think about a single identifier, you should work with combinations. So in the ideal case, you're actually getting the request, and you're actually using, for example, Dataflow to cluster through the combinations of requests, being able to identify a particular one which is driving the score up, and then deciding on this particular fingerprint. But something that really stuck my impression was that IP address, you would imagine that people are going to just randomize them and use hundreds of proxies. That's almost never the case for web application attacks. It is the case for other types of abuse. Another question?
Thank you.
Well, thank you very much.